just want to know what is the field of this one. If I just go out of camera, okay, I can just move around as you, yeah. Start. Yeah.
Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RVCCPS IASC. It's my pleasure to introduce today's speaker, Professor T.G. Venkatesh. He'll be speaking on design and performance analysis of medium access control protocols for multi-packet reception. Professor Venkatesh received the BE degree from Annamalai University, ME degree from Bharatiyar University. While working as a scientific officer, he obtained his PhD from IISc Bangalore in 1993. For a brief duration, he served at the Center for Development of Telematics and Indian Space Research Organization, Bangalore. He was a faculty at the Indian Institute of Technology, Delhi from 1994 to 1999. Presently, he is a faculty at the Electrical Engineering Department of the Indian Institute of Technology, Madras. He has authored 2 books. His areas of research include stochastic modeling, computer architecture, and various issues of wireless networks, and applying game theory and machine learning techniques to the design of wireless networks. Over to you, Professor.
Thank you. Thanks for the introduction. Let me begin by thanking the CNI for asking me to talk and giving me an opportunity to share my research problems with you. So essentially what I plan to do in this talk is to talk about the design and performance analysis of medium access control or MAC protocols for channels supporting multi-packet reception. By the way, I belong to the Department of Electrical Engineering, and this research has been carried out along with my MS and PhD research scholars, and I am here because of them. So needless to say that I thank them. Well, so today with the advancement in physical layer technology, it is possible that you can receive more than one packet at a time by a receiver. So this is what is called as the multi-packet reception. And there are various techniques that make it enabled. For example, the successive interference cancellation is a technique where you decode one packet and then cancel it and then decode the next packet in the power domain, and then successively you can decode it. You have got MU-MIMO, MU-OFDMA, and so on. So all these techniques really boils down that multiple packets can be received. So we concentrate here on the MAC layer design. So if you want to fully utilize the advantage offered by the physical layer and leverage the increased rate that is being offered, you have to redesign the MAC protocol. Unless you redesign it, it will become the bottleneck and the network as a whole will not have a better performance. So we in our group have been looking at these issues, and started redesigning the MAC protocols for channels supporting multi-packet receptions. We started off with the basic and probably the basic and the fundamental protocols like the pure Aloha and then CSMA and then the even the protocols that are suited for M2M communication like dynamic frame slotted Aloha, and then the CSMA CA, which is the backbone for the IEEE 802.11 series of standards and so on. So this is what I'm going to plan to share with you. So we will start off with Aloha analysis. That is, before that we will start off with what is our channel model for all the MPR MAC protocols that we are planning to do it. So we have a network which has got an infinite number of nodes, and each node is independent of each other in generating the traffic, and the packet generation process can be treated to be a Poisson stochastic process, and the aggregate process is also Poisson in nature. We can have two kinds of packets being thought of, one the new arrivals and those which are being backlogged and then tried again. So the aggregate process is Poisson in nature. That is one thing. And we assume that the packet is a fixed size. Packets of varying size can also be treated, but it will only make the analysis little involved, but this is not a restricting assumptions. Then the most important thing is that we have to have a model for this physical layer mechanism which offers the multi-packet reception capability. We use a model which is called the K-MPR model. So wherein if we have multiple packets being transmitted at the same time, all these packets will become successful as long as the number of packets being transmitted is less than or equal to a value called as the MPR threshold. We denote it as K. So K is the number of packets that can be simultaneously transmitted in the channel. If more than K packets are under transmission at any given time, all the packets will collide and none of them will be received successfully. So it is a hard threshold case where up to K the channel will support transmission. Just after that everything will collide. So that is the K-MPR one. The reason that we use it first is that it is analytically tractable, of course, and we have another model which is called as the generalized MPR model, wherein instead of putting a hard threshold, what it will say is, supposing I packets are being transmitted, what is the probability that J out of I will get received correctly? It assigns a probability for different values of I and J. Of course, it cannot be infinite, so it puts again a threshold on K, the maximum number of transmitters that can be treated. So it forms basically a matrix of I by A. So within that, if I packets are being transmitted, what is the probability that J, which is less than or equal to I, will be received successfully? Those probabilities will be the entries of this kind of a matrix. This is called as the generalized one. But we will be dealing only with the K-MPR model. Although generalized MPR is general in nature, for our purpose K-MPR would be suited for a reason that eventually at the MAC layer we are interested in statistical averages like the average delay, the throughput and so on. Even if you use K-MPR, generalized MPR model and arrive at the different probabilities of different packets become successful under a different transmission condition, eventually we have to average it. So it is possible that for a generalized MPR model given by a matrix, it is possible to find an equivalent K and use the K-MPR model. So that is the whole idea. So with this one, we are going to derive the analyze all the protocols. The main performance metric that we are interested is in the throughput, which we denote it as S, and it is given by the average number of packets successful per unit time. Okay, again per unit time, because we saw that the packet length are fixed, so we can as well take the length of the packet to be 1. So the number of packets being transmitted successfully divided by 1 is the throughput. Again, so it is the average number of packets successfully received, okay, per unit time. So that can be arrived, the throughput can be arrived as the rate at which you transmit a packet, that is given here, multiplied by the probability that a given transmission is successful. So the rate is something that we know out of the model. The only thing that we need to calculate in the whole analysis is the probability that a given packet, which we will call it as the tagged packet, to become successful. So first we will start off the Aloha protocol. So let us look at a packet called as the tagged packet and look at under what condition it can be successful. Okay. Before that, quick reminder of what the Aloha protocol is. There are a large number of nodes. Any node that get a packets at any given time can immediately transmit. No need to wait. And if it gets collided, because if it doesn't get the acknowledgement, it will treat it as a collide one. The packet becomes a backlogged one, and therefore it has to be retransmitted. So the node will wait for a random amount of time before retransmitting. Why? Because an immediate transmission means a guaranteed collision. So it has to wait for a random amount of time and then transmit. So this is how it will happen. So we have fresh packets and backlogged packets all being attempted with a rate lambda. So this is the Aloha protocol. So let us look at a tagged packet and only concentrate on the success that this tagged packet can achieve. Okay. So that is marked in this color, orange color. So if you look at this of unit size, so you will see that around this tagged packet there is an interval of size 2. The packet is of size 1. There is a interval of size 2 starting from tau minus 1 to tau plus 1. If this tagged packet's transmission starts at tau, this is the region of vulnerability. Any other packet that gets transmitted within this interval has a potential of will collide with this one, definitely. Because it is obvious, anything that starts after tau plus 1 is not going to collide. Anything that is started before tau minus 1 is definitely will get over before tau. So this is the interval of vulnerability. So we should only concentrate on those packets whose transmissions are started in this region of tau minus 1 to tau plus 1. Again, for the sake of understanding, we will divide this whole thing into two intervals, I1 and I2. I1 between tau minus 1 to tau, I2 tau to tau plus 1. Let A1 be the number of arrivals in the interval I1, A2 in the interval I2, and these arrivals can be given a name. Let me call it as, and we define a random variable. Let x1, x2, xa1 are the random variables defining the starting of the packet 1, packet 2 and so on from the beginning of this interval. That is, if a packet, this is the packet we are talking about, then this time is what we call as the x's, x1 or x2 or x3 based on the packet. Okay. Similarly, y1 is this one. This is the beginning of tau to this one. So we have got A1 arrivals in I1, A2 arrivals in this one, and we are going to analyze these things. Before we even analyze it, we will start looking at the bounds that we can talk about this one. The first thing is that the slotted this Aloha, this is not slotted Aloha, this is pure Aloha. Okay. For this Aloha, the lower bound, that is the minimum throughput that is possible, has to be this one. Because what happens is up to k packets can be transmitted in the k MPR channel model. So given a packet, it can tolerate up to k minus 1 interference. That is what is very clear. So anywhere in this vulnerable period, if there are k minus 1 packet transmissions, then this packet will be successful. So if you, the slotted Aloha, this is the minimum throughput it will achieve. This is the transmission rate and this is the success probability. That is, this is a case where up to k minus 1 packets are being transmitted. This is the probability that I packets are transmitted based on a Poisson statistics. That is, the interval is of size 2, rate is of size rate is lambda, 2 lambda is the Poisson parameter. So the probability that this Poisson random variable takes a value, okay, I is 2 lambda power I e power minus 2 lambda by I factorial. So up to 0 to k minus 1, this is the probability of success with this rate, and this much of throughput is guaranteed. And this is the maximum guarantee that is allowed, that is the upper bound. The reason is, see, in this interval, if there are k minus 1 other transmissions, that is the maximum that is possible, because including this tagged, only k is possible. Similarly, here also maximum of k minus 1 only is possible. Okay, again the best case will be all these k minus 1 starts and ends here, all these k minus 1 starts and end here, so that here there are k, that is the best that we can think of. Beyond that it will be a guaranteed collision. So with this as the rate, and this is the condition that in the earlier interval of size 1, there is only up to k minus 1 transmission, 0 to k minus 1 lambda power I, because size interval is 1 and rate is lambda, and this one. This is for one interval, this for another interval, that is y square. This is the two bounds of this one. Incidentally, the slotted Aloha becomes very, very simple. Because if it is a slotted Aloha, what does it mean? Packets can only start at certain points of time. For example, if you say that packets can only start at this point of time, all packets of same length, then they have to get over by this one. The only condition that we have to put for this tagged packet to be successful is not more than k minus 1 other packets are there, this one. So that is this one. So this is a very, very well known one. There is nothing this one. So this slotted Aloha's, actually pure Aloha's, this one lies, this is greater than this one. That's what we basically do. So that is all about the bound. Okay. Something more if you want to talk about, now what we will do is, we saw that we have certain random variable x1 to xa1, which mark the beginning of the packets 1, 2, 3 to a1 in this interval. Okay. Now we can look at the order statistics of these random variable. Okay, which is marked with, usually our order statistics are marked with this symbol. X of I indicates the ith order statistics of the random variable x1 to xa1. So what is x of 1, order statistics 1 is the minimum of the random variable x1 to xa1. X of 2 is the second minimum, third minimum, and so on. And x of a1 is the maximum. Yes.
Throughput of slotted Aloha, it's greater than the throughput of the Aloha, which is continuous one. The equation 3, you're saying that the throughput of slotted Aloha is
greater than or equal to?
Greater than or equal to slotted Aloha.
Yeah.
So what, isn't it counterintuitive when, say, when you have a slotted Aloha, you can only transmit the boundaries. But whereas Aloha, you have a period of...
in Aloha, anywhere, anytime you can transmit.
Anytime you can transmit. So
that has always been the case, even in collision channel model. Sorry, I should have mentioned about the normal one, which is the collision channel model. Always the maximum throughput of Aloha is 18%, and slotted Aloha is double the size, which is 36, which is a well-known result. Yeah. So we look at the order statistics of these random variables as well as the order statistics of these random variables. Okay. That is one thing which we will make use of. Okay. So now what we will do is, first thing what we will do is, there are x1 to x2 a1 are the arrivals in this interval. These are all Poisson arrivals.
So how are you able to transmit k of them without collision? Because you have k channels, or k packets, how are they not colliding?
Because that is what the physical layer, we assume that physical layer offers the capability of multi-packet reception.
Okay, got it.
And we model that up to k packets, if transmitted, they will not collide.
Correct.
More than k, it will definitely collide.
And what is this random variable x1, x2, xai, and y1, y2, yai?
These random variables x1, x2, or if there are a1 arrivals, this is the time from the start of this interval to when these packets arrival take place.
Okay. But I thought since it's slotted Aloha, we
are not discussing, it's only Aloha I am discussing.
Okay, because for slotted it will always start at the beginning, right?
Correct, yeah.
Okay, thanks. And in slotted, your length is also fixed.
Length is also fixed as well.
Thanks.
Yeah. So, first thing is that these are all Poisson arrival. We know that from the uniformity property of the Poisson arrival, given that there is an arrival in this interval, the arrival... The length of all packets are taken to be same, which is equal to 1.
Identical. Okay.
Identical. That is again for the analytical tractability. Okay. So given that the arrivals are all Poisson, okay, then the arrival time of Poisson random variable will be uniformly distributed over this interval from the uniformity property. So all these x1, x2 to xan, similarly these are all U01 processes. That is one thing. Then they are the order statistics. X of I is the ith smallest from the set of A1 uniform random variable, similarly J. Then what we are interested in, we are interested in finding how many, the maximum number of given certain number of arrivals that is characterized by the capital A with the whole vulnerable interval of time 2, and given A1 and A2 the number of arrivals in the earlier and the second one, what is the maximum number of interference that can occur? That is what we know for an arbitrary values that are given. That is what we are basically interested in finding it. First thing is that because the packet can start anywhere, it will be difficult to, given this one, what you have to do is at any given time, if I saw a vertical line during the tagged packet transmission, if I find anywhere more than k-1 interference, then this whole packet is gone. So that is what I have to do. So I have to keep searching over the whole interval, which is very difficult. To analyze it better, what we are interested in, to find those packets that are non-overlapping, those packets which might be involved in the interference, which are non-overlapping. Why I am interested in non-overlapping packet, for example these two are non-overlapping packets, is because the effective interference they cause to the tagged packet is just 1 and not 2. Because they are non-overlapping, they can interfere with the tagged packet only at different time points. So if you have any non-overlapping packets, I can assume that it is one interference is the maximum they will cause. So every such pair will cause only one interference. Among all the packets that interfere, that is which have arrived in this vulnerable interval, identify pairs such that they are non-overlapping. For each pair I will take account of one interference. And after I exhaust with all such pairs of non-overlapping, the remaining one will cause one interference. I will add up all together, and as long as this is less than k-1, I am successful. So that is why I am interested in non-overlapping packets. Well, if you have a non-overlapping packets, two such non-overlapping packet, one has to start in this interval, another has to start in this interval. Two packets starting in this interval will overlap. Same is true for this. So assume an x of x1, x here and y. Let us say one order statistics xi that start at this point, another order statistics of y, yj you call it, that start at this point. Then you see that this is xi, so this has to be 1 minus xi, and this is yj, that is the starting of this packet from the beginning of the interval, which is the jth order statistics like this one. So the condition they have to be non-overlapping is sum of these two should be greater than 1. Because the length of the packet is 1. So 1 minus xi plus yj has to be greater than 1. I can rewrite it so that x of I should be less than y of j. That is, this order statistics has to be less than this order statistics. So this is what I am looking at. And now the idea is to find the maximal such pairs of non-overlapping. That is what it is. There can be many such pairs. That is what we are looking at. So let us identify, suppose we identify a set of non-overlapping pairs, non-overlapping pairs, call it as D, okay, and its cardinality is D. There are D non-overlapping pairs. This is the maximum number, I can find it in the one. Then we can find one more random variable W, which is the maximum number of interference that this tagged packet will suffer. So that is given by a relation W is equal to A minus D, where A is the total number of packets that has arrived in the vulnerable interval. The proof is very, very simple. This can show. See, there are, suppose D is the maximum number of non-overlapping pairs. Okay. So there are D non-overlapping pairs are there. Okay. Then out of A arrivals. Okay. So the remaining unpaired one are A minus 2D, because each pair has got two packets. D such things are there. So A minus 2D are the unpaired. So for this tagged packet, the number of interferences are A minus 2D plus D. which is A minus D. So this is the maximum number of interference this packet will suffer. So I am interested in this random variable. I will find the CDF of W and then evaluate the CDF at the K MPR threshold, which means that W is less than or equal to K minus 1, then that is the probability of success. That is the trick that we are going to use. So if we can find the cumulative distribution function of the random variable W, which is the maximal number of interference that this tagged packet can suffer, but you have to give a condition that there are A1 arrivals in the earlier interval, A2 arrivals in the second interval, then this is what we are interested, because that is the success for the tagged packet. You can see that there has to be up to this A minus W is the D. There has to be D non-overlapping pairs. The condition for a non-overlapping pair we have seen is X of I has to be less than or equal to Y of J that we saw. I will tell you how this comes. So now for that to happen, you have got two non-overlapping pairs. One is in this one, another is one. I will take the first, let us say D non-overlapping pairs are there. I will take the first D order statistics from the earlier first intervals and the last D order statistics from the second interval, and they should be non-overlapping, because if I take anything before that, they will be overlapping. So these two are the farthest apart. Even if this is not happening, any other order statistics which I take is bound to overlap. So if I say there are D non-overlapping pairs, it is guaranteed that those D should be such that the first D order statistics from the earlier interval and the last D order statistics from the last interval should be non-overlapping. Okay, so X of I should be less than or equal to, the condition X of I has to be less than or equal to, actual thing is A2 is the number of arrivals in the second one, A2 minus of D minus 1. Okay, this 1 means it has to be D minus 1, 2 means D minus 2, okay, I means D minus I. So that is what basically it is. A2 minus of D minus I is what it is. That is translated to A2 minus D plus I, and then you can rewrite it as this one. So this is the condition that we have to look for evaluating this one. I will tell you using a simple example. So here is the tau, and this is the tagged packet, and tau to tau plus 1, tau minus 1 to tau, and you have got different packets that are being arrived and so on. 1 starts here, ends here, 1 dash starts here and ends here. So 1 and 1 dash are non-overlapping. If you look at 2 and 2 dash are not, they are overlapping, because they are overlapping here. Similarly, and so on. So I can form a non-overlapping pair in different things, but I am interested in the one such maximal set. Anything beyond pair, if I put it, they will be overlapping. This is one such pair, 1 and 3, 2, 4. 1 with 3 and then 2 with 4. I could have clubbed 1 with 2, then I cannot form the other one. So that is how I have to maximally choose. Okay, this is what you have to do, and for this you see this condition will obey. The number of non-overlapping pair is 2. A is the total number of arrivals. For example, here there are 3 packets 1, 2, 3. Here there are 4 packets 1, 2, 3, 4. A1 is 3, A2 is 4. Total sum is 7. So 7 minus D is the W, the number of interference it can happen. That will be 5. So this is just an example. So what it shows is 5 is the maximal interference that is supported. So if my MPR threshold is 6 or more than that, then my tagged packet will be successful. So this example illustrates that. Well, now once we know this FW of this one, then the throughput can be easily arrived, but computing that itself is involved. We will see that later. So what I will do is, suppose up to K minus 1 interferences are allowed. So FW of W indicates the cumulative, FW is the maximum number of interference that can occur. Random variable representing maximum number of interference that can occur. That has to be less than or equal to K minus 1. So which means that the probability for this to happen is evaluate this FW at k minus 1. Okay, and we always can find only FW conditional CDF given there are I in the first interval, A minus I in the second interval, together they are I. So that is what we will be able to find out. Okay, well, for I to occur, so for overall I to occur in the full vulnerability interval, I to occur in the earlier interval and A minus I to occur in the second interval, the probability is this one, A, I, 1 over 2A and so on. It's a very small binomial one. And this I can range only between this because both I as well as A minus I has to be less than k minus 1. In both interval, maximum interference allowed is k minus 1. That is why this funny limits that occur here. So this is how the probability of success is. Once we know the probability of success, then the throughput can be easily arrived written like this one. Why? As long as there are only totally k minus 1 packets in this whole interval, they are all going to be successful. So 0 to k minus 1 in an interval of size 2 is always successful. So 0 to k minus 1, 2 lambda power I, this one. So this is a guaranteed one. This is the probability of success. Under these events are successful, multiplied by the rate will give you that will be a throughput combination. And for the other one is beyond k minus 1. Okay, so onwards, beyond k minus 1 onwards, the maximum that is allowed is also, I know, it is 2k minus 2. Because we have already seen k minus 1 is the maximum that is allowed. So the maximum is also 2k minus 1. Within this one, what is possible is this I gets split into j in the earlier interval, I minus j in the second interval, and that CCDF for W, if it has to be computed at k minus 1, okay, this will be the probability of success. And for this I to split into 2, for I to occur, this is the Poisson probability. So this is the case when between k to k minus 2 to occur with this probability and they become successful. This is nothing but this formula. This is nothing but this formula. So it will be successful. This is what we have seen. Well, now computing, this is a case for a generalized MPR channel model, which I will skip, which is not this one. And this is for a case of the finite node. There is nothing but, see, instead of nodes having arrival rate lambda 1, lambda 2 and so on, then how do we find it? Then what we will do is this will be the throughput formula. Because why? Because the ith packet throughput is nothing but its own arrival rate, but the arrival rate of others, because the same node cannot collide with other. Packets are generated one by one. So this is the arrival rate of packets other than I. So this is the throughput formula which we computed earlier for other arrivals given the MPR model divided by this. So this would be the throughput offered by I, and then you sum it over all nodes, and that will be the throughput if we have heterogeneous nodes. Well, computing this formula, FW of W given A1, A2. To recall, W is the maximum number of interference that a tagged packet suffers. We are computing the conditional CDF of W given the condition that A1 arrivals in the earlier and A2 arrivals in the later interval. And what is the condition? That the first D, okay, order statistics in X and the last D order statistics in Y should be non-overlapping. The condition for each non-overlapping is X should be less than corresponding Y. So X of 1 should be less than or equal to Y of A2 minus D plus 1. X2 less than or equal to this and so on. So these are the condition. If it is obeyed, then that is the condition basically. So now what we will do is, there are A1, okay, we will take the 1 to D, okay, of X, okay, that is one set omega, and A2 minus D all the way to A2, the last one as another set psi. So you have two sets, the one for defining for X, another defining for Y. I am defining two sets, omega and psi. First D and then last D in the next interval. So This can be written as this one. Supposing if I put a condition on the value taken by the random variable y as small y, then if I evaluate it, I can then evaluate it. Nothing but this is the CDF, joint CDF of all these random variables x of omega, omega belonging to this set 1 to d. This is the joint conditional CDF of the first d order statistics of x. Evaluated I, given that these take these values, and then uncondition it by taking an expectation over the values of y of psi. So I am finding a conditional CDF on the joint CDF of x of omega, taking that the values of this to be given, and then uncondition it, that they can take all possible values by taking the expectation. So one is the computation of the joint CDF, another is the joint PDF, and then integrating it over. So that is what you have to essentially do, and if you do that one, you will get this formula. This is the joint CDF conditional probability, and this is the joint CDF conditional probability, and with that one you will be able to arrive at this one. And because this is an order statistics of uniform random variable, it is much easier. You have very good formulas. If you have other random variables, it will be very difficult. Okay. For example, with regard to computing an successive interference collision, we had a problem of finding correlated exponential random variable, and you have to find the order statistics, because we want to know which of them, we have to arrange them in the order of level of their power, okay, to find which is the strongest and remove it and so on. Finding that is very difficult, because it looks like from the mathematical literature there are no closed formula for the joint CDF or PDF for the exponentially distributed random variable, which are not independent. Okay, so this is what we do, and then with that we are able to find out the formula for the throughput for the pure Aloha for different values of k. Different values of k is equal to 2, 3, 4. These are the formulas. Okay, and so to be correct, the Aloha protocols formula has been derived in 1970, and after that, after 50 years, this exact formula has been obtained. Before that, there are only approximate. Only exact formula for k is equal to 2 was existing in the literature, and this is valid for arbitrary value of k. And these are the bounds. For example, the actual theory gives you this. The upper and lower bound gives for different values of k. K is equal to 4, k is equal to 7, just to show how these bounds are. And these are the plots of the analytical and simulation results. Analytical results obtained by that formula. For example, these formula. For example, if it is 7, this is the formula that we have been using. And simulation we have obtained through MATLAB, and we have plotted it, and we get an for 7 also, you can see that we get an excellent match of this one. So that formula works. Well, now we will go to the next one, which is the CSMA protocols. There are two versions. One is the CSMA, which is the non-persistent CSMA, and another is the one persistent CSMA. So for example, if you look at the way it works is, if the channel is idle, then a node senses the channel. If it is busy, it will not transmit. It waits for the channel to become free and then only transmit. But moment the channel becomes free, if a node transmits, then what can happen is, the transmission made by a node will reach other nodes at different time points. It is so happened that after the transmission of one node, some other node may still perceive the channel to be idle, may also start the transmission. So there is a period, there is an interval of size A, which is the maximum propagation delay of electromagnetic signal or whatever it is within the entire channel. So this interval is an ambiguous period. There is more than, because different nodes perceive the channel to be idle or busy, more than one transmission can occur. Okay, and that can cause collision. So suppose an idle channel gets over, that is, there is an arrival at this point, therefore the channel is no more idle and its packet transmission starts, which is of unit length. After it stops, there is a period of A in which different nodes will perceive the channel to be idle or busy at different time points. After this A, all of them will perceive the channel to be busy and they will not transmit. But during that A, there can be one or more transmissions. This is what can happen. So this can be busy, and this is a period in which transmission can occur. After that, so this is a duration where it can be busy if there is only one such transmission. You also have a case where once there is an idle period gets over and there is one transmission that is started, and within a duration of A, there are two more transmissions that has also got started. So all of them will proceed. So when will the channel become free? After this last one time unit after the last attempted transmission. After this third one, after this only the channel will become idle, and different nodes will sense that after a time of A. So the busy period will be of length 1 plus A y plus A, but y is a random number which is not so easy to calculate, because in this interval different nodes will transmit, and what is this duration within the A when the last such transmission attempt has taken place? That is what we have to find. So this is again the busy interval and so on. The duration of idle interval is very simple, because they are Poisson arrivals with a rate lambda. Idle period will be exponentially distributed and the average value is 1 over lambda. That is easy. Where the busy duration is something that we have to find, and you can apply the renewal reward theory. You find the renewal intervals and find the reward within that interval and find the average reward. Reward is nothing but the number of packets being transmitted. So we will see that in an interval there can be up to k as long as the number of packets I transmitted is less than or equal to k minus 1. Apart from the tagged transmission, they all will be successful. So this many packets can transmit, that I plus 1 into lambda I power I, this one. This is what can be the reward if I such things transmit. Okay, this is the probability that I such transmission bounded by 0 to k minus 1 will go on. This is the success probability. Apart from that, the tagged packet will transmit. That will be lambda into S. Okay. What is the duration of the packet? Duration of the interval? Okay. That is 1 plus y plus A. So it is 1 plus A plus this y can be found out. We will not get into it. That will be 2 minus some value. So the length of the interval will be, an idle is always followed by a busy, followed by this one. The length of the interval is, renewal interval is starting from here to end. It is 1 over lambda plus this value. So that is what is given here, 1 over lambda plus 1 plus 2a with this small correction. So this is the renewal duration, this is the reward, average reward is this. So that way you can find it, and you can plot it like this one. For different values of, this is the aggregate arrival rate as it increases, for different values of A, okay, which is the vulnerable period duration, not vulnerable, that ambiguity period duration, okay. Where 1 is the packet transmission time. In terms of that scale, A can take a value of 0.1, 0.01, A1 and so on. So you say if that is 1/100th of the actual packet transmission duration, the throughput can be maximum. If it is 1/10th, then this is what will happen. So that is what this one is. If it is equal to this one, then it will saturate like that one. Okay, this is happens for a k is equal to 4. See, for a k is equal to 4 MPR threshold, 4 packets can go. But even then, if A is equal to 1, which is equal to packet duration, then the throughput itself is not even more than 1. That is what happens. And even in this case, the best throughput that is achievable is something like 2.2 or something like that. Not 4. You can't go to that level. And this is actually for against the carrier sensing delays for different values of k is equal to 1, 4 and so on, against the arrival length. So we will just leave it. Then there is one more protocol. So that is given by this one, that is the one persistent. Again, I will try to cut short this one, we have other things to go. So basically here what happens here is, when a packet arrives during a busy period, then it will wait for the channel to become idle and will definitely start. So at the end of a busy period, number of packets which have been waiting will start, and therefore it's not a good strategy, okay, so and therefore the collisions will be large. But again, this is one fundamental mechanism. You can have a p-persistent protocol which is either non-persistent or one-persistent. To analyze that, we should know this one. There are three kinds of types of transmission go on. One is the so-called idle, which we know. Another is the one where the busy period is initiated by one transmission. Then the duration will be 1 plus A, okay, plus another A in which other packets wait and transmit. Then there are type 2 transmissions in which during the, I think an idle period got over, during this A, 3 packets have arrived, they all they would have started, and during the busy period also 4 packets arrive. All of them will transmit when you sense the channel to become free again. Okay, so this is what will happen. This is the type 2 one. So you can model these 2 types of these durations, okay, to be a Markov chain model, type 0, type 1, type 2. From type 0, you always go to type 1 because after an idle period, you always start off with a type 1 transmission. One packet will definitely start and so on. And then you can solve this Markov chain model and arrive at the throughput of it. I will not just get into all these things, and its formula plot can also be like this one. This is the one persistent protocol for k is equal to 4. You can see that the throughput maximum that is also less or about 2 only. Well, now we will get into a more interesting one. Well, these are all classical protocols. Now we will get into a more useful or the practical protocol, which is the 802.11 protocol, that is based on the CSMA bar CA protocol. Okay, so what it does is, there we have got a number of nodes, and let us look at all these 802.11 A, B, everything has been designed for a collision channel model, okay, where only one transmission is allowed. If it is an MPR channel, how we should redesign the 802.11 protocol all the way from A, B, N and all the way to AX and so on. That is what we will look at. Okay. To recall, the MAC protocols, the collision channel model is the number of transmission that is allowed. Okay, that is okay. We will come to that one. So in this KMPR, the adaptive backup protocol, we will have a look at how the adaptive backup works for 802.11 protocol. That is, for node on getting a packet, senses the channel, and for a period which is called the DFSA interframe spacing. If the channel remains calm or idle, then it makes a transmission. Otherwise, then it backs off, selects for a random amount of time. How does it select for random amount of time? Because the time is slotted, it chooses a counter value randomly and decrements 1 per slot until it reaches 0. So the count value that it chooses is drawn from a collision window, which is initially a value which is called as the collision window minimum, and every time there is a collision, it doubles. That is the back off till the collision window becomes a maximum CW max. From CW min to CW max, every time you double for every time you encounter a collision. This is how it works, and when there is a transmission, immediately this back off procedure, decrementation of the counter, is being frozen. Okay, if it is not frozen, all the nodes will be counting to 0 and they will start the transmission at the same time. So whenever the channel becomes busy, the count off is being frozen. This is what the normal 802.11 protocol is. Now what we propose is that we have a channel which is MPR capable, can support up to say k transmissions. Then why do we decrement the counter value by 1? You can decrement by more because the channel allows more than one transmission. Okay, so how should we decrement is the question. So for that, if k is the maximum number of transmissions that are possible, if you can estimate the number of ongoing transmissions and say call it as I, then k minus I additional transmissions are allowed. So you better decrement the counter by k minus I, where k is the MPR threshold and I is the number of ongoing transmissions. So that is the adaptive procedure that we recommend. So decrement the counter based on the channel utilization, that is k minus y. But if the number of transmission is more than a certain value, okay, you have to freeze the count off. You can set that value to be k, or you can set that value to be a different value, kt less than k. Okay, that we call it as the pseudo MPR threshold, because Actually, not using K for freezing, but a lesser value is more beneficial, which can be seen. So if that is what is this simulation result shows that for a normal legacy 802.11, this is the back-off procedure, this is the throughput it offers around 2. When the MPR value is 4, it offers 2. That is because it only decrements by 1. But if we decrement by more than 1, by K minus I, and use the threshold to be different value 2 and so on, you get higher throughput. That is what we see. But again, beyond a point, there is a law of diminishing returns, you don't get anything. 2 and 3 offers nearly the same. Similarly, if you look at delay also, so the delay for the legacy is KT is equal to 0, okay. So then it is maximum. For other 2 and 3, it is much lesser. So that shows that the adaptive back-off procedure is much better. Now here comes the analysis of the adaptive, this is also similar thing. Adaptive back-off procedures analysis. What we in a this is a modification of the so-called Bianchi's Markov chain model, where we do an analysis of 802.11 protocol by decrementing the count off and so on. So we saw that what will happen is we start off with the back stage 0, where there is no collision, and we initialize the counter value to a value from 0 to the maximum 1 and decrement by 1 whenever the channel is not busy, and so on. When the count off becomes 0, you transmit. That is the legacy, the Bianchi's one. But here what we have to do is, we freeze the count when the number of ongoing transmission is more than the threshold KT and not just 1. So this it has to be redefined. When the channel becomes free and busy, has to be redefined as only when the number of ongoing transmission is more than KT, the channel is treated to be busy, and then only the count off is being frozen. That is number 1. Number 2 is that you decrement the value by a certain number of values, not just by 1, by certain number of values which can be varying dynamically. Okay, so it will happen that from here you will decrement by a value to, from 1 you will decrement to d minus 1, again you will decrement to something, and so on. So the decrementation process will be in terms of some value which is not just 1 by d and so on. So start off with 1 value, decrement by 1 minus d minus 2d and so on. Another thing. Third thing is that because of that one, you may reach a count value which is less than 0 also. From 2, if you decrement by 4, you can get less than 0. So we have to redefine the condition for retransmission. Whenever the counter value becomes less than or equal to 0, you have to retransmit. And there will be a set of nodes here. For example, all these nodes, as after one decrementation, if d is the decrementation value, after one decrementation will reach this state which is less than or equal to 0. So they will only decrement once because their decrementation value is d. So all these states behave identically. We can call it as a set S0 and treat them together. Another set of states from d plus 1 to 2d, okay, minus 1, they all will become identical because they will decrement by 2 before reaching this less than or equal to 0 states. So we can club these states into S0, S1 and so on and make the analysis simpler. So that is what we have done here. So we have, this is the beginning of a transmission. So what we do is, every value will initialize to a value of to the one of the counter values, and if W0 is the collision window size, initial collision window size, 1 over W is the probability that a counter value will be initialized to that value. But we will fall in a set having d such counter values. So d by W0 is the probability with which you will end up in one of these set. And with a probability PB you will freeze it, that is more than KT satisfaction, 1 minus PT you will go like this one. When it becomes 0 you will transmit. That is one thing. One more thing is that here, when in a collision window normal one, once a packet transmission starts, it is bound to be successful, because once it starts it will make the channel busy, no other will even attempt to transmit. But here in MPR model, what we do is, Even though there are transmissions, we will decrement, we will not freeze the count off, we will decrement, and more transmissions can be attempted. Until it becomes more than up to KT, we will keep attempting it. And it may so happen that many of them, K minus KT may transmit and may cause collision. So even after a transmission, a collision can occur because the count off is not frozen and it can do it. So we have to define two states. One is a state in which the packet is being transmitted. Okay, so far it has not encountered collision, and moment it encounters collision with the probability PC, it will get into a state, this one. Okay, so this is the actual collision state, this is the transmission state. And to make this process Markovian, we assume that packets is of size, average size of L slots, and therefore to achieve that one, we will assume that in every slot, packet transmission ends with a probability 1 minus L and continues with the probability 1 minus 1 by L. So then the average will be L. So that is what we will do. So that makes it Markovian. So with the probability 1 by L in the transmission 1, if the transmission ends, it becomes successful. You go to the 0th stage and take the next packet being transmitted. But on the other hand, if there is a collision, you get into the collision state, but you will continue to transmit because you don't know collision has occurred. And when the packet transmission stops with a probability 1 by L, you will increment or go to the next stage by doubling the collision window and going through that one. So this is how it happens. When you reach the last stage, anyhow, if there is a collision or success, in the case of collision, you will discard the packet. In the case of success, you will go and take the next packet. So this is the corresponding Markov chain model, and we can solve it. We will not get into it, and then this is the usual way of solving such Markov chain models, and you can arrive at the probability of the transmissions and throughput and so on. But here we have assumed that the number by which you transmit, okay, by you decrement is D, which is the difference between the K and the number of ongoing transmissions. But the number of ongoing transmission can be dynamically varying, and therefore that decrementation is not uniform by 2, 2, 2 and so on. It can be 2, 3, 1 and so on. So we have to model that. For that we use another Markov chain model which models the channels number of ongoing transmission in that one. If there are n nodes, it can vary from 0 to n, and these are the probabilities with which that we can see the number of transmissions can occur. Suppose this tells that, supposing I is the number of ongoing transmission, for it to change it to j, the probability is this one, because when there are I ongoing transmissions, there are n minus I nodes which are not transmitting. Any one of them can initiate a transmission. Let us say j of them transmit. Probability tau is the probability with transmission, tau power j, and others keep quiet, 1 minus tau power n minus I minus j. So this is the probability with which, while there are I transmissions, j additional transmission can begin. Similarly, R of I comma j indicates when there are I transmission, j of them stop their transmission because packet got over. How? Out of I, j of them stop with this combination. 1 over L is the probability that the packet transmission gets, j stops while others continue. Once we have these two things, then we can find the probability that the state can go from I to I plus m. State the number of transmissions to increase from I to I plus m. One way is that is from I, m plus j additional transmission are started, out of which j are being terminated. Then again it will be I to I plus m. This is one way. The other way is I to I minus m is m plus j terminates and j starts. Then also it will be m additional transmissions. These are the two ways in which it can happen. So accordingly we can solve it using this usual thing, pi is equal to pi p. So pi, the stationary probability vector, is a left eigen vector of this transition probability matrix and so on, the usual things and so on. So again this also, I think I have to stop, I will cut this one. We can get all these things, and this is the throughput that is achievable. For example, here the MPR model is 5, CW minimum is 0, and if you use our adaptive protocol, you can achieve a throughput of saturated throughput of 3.5. So this is what is achieved Similarly, here what we've shown is for various MPR threshold, the maximum achievable throughput increases like this. Okay, for 2 it is less than 2, 4 it is about less than 4, even for a MPR threshold of 14 it is only 7. So only half of it is what is achievable. So this is what I will say. So we finally, there is also one more, I will conclude with this one. That is, there is an enhanced DCF, ADCA in 11 AAC. So wherein what happens is, there are different traffic categories and each of them has to be serviced differently, namely the voice, video, best effort, file transfer and so on. And that is being achieved by reducing this amount of time they have to, arbitrary interframe spacing, amount of time they have to wait before transmitting, and having a lesser collision window. So the random time they wait is also less, they will get a chance. This is how service differentiation happens. But we can play around with other things like when we freeze the count off, KT can be K-1, which is the largest that is possible for this high priority one, or it is half of it, or it is 1/4 of it, or is the legacy one. So this is the condition when we freeze the count off. So here we more often will freeze the count off. Here and all the freezing will not happen easily. So they will have a better chance of access. Okay. Then the number by which we will count decrement is also K by minus L for these two, and here only we can decrement by 2. So this is also a way of achieving the service differentiations. So that's it. I will stop if there is nothing more. I have certain things on 802.11ax. The same decrementation process also holds good for 11ax, and we have derived the throughput and other things for that also. So I have any questions, I'm open to.
Thank you, Professor, for an interesting talk. Are there more questions from the audience?
So in this this setup, when you have the mix of different ways you decrement and increment, for that the analysis will be much more complicated, right? Because your
Yeah, correct.
So do you have any analysis for that, or you just
Analysis.
For this case when you have mixed of these?
Oh, this one.
Yes.
Yeah, no, we have not for this this kind of an enhanced one. We have not done it.
Okay.
For the normal one is what I have shown it.
Okay. So to me it seems clear that if you have a homogeneous, protocol, right, it's easy to analyze because
Correct. Yeah.
your Markov
Correct.
chains are going to be
Correct.
similar.
Yeah.
But this
All
one
these
will be
things.
very
Yeah.
complicated, right? Because things can go in different.
Correct. This one we have not analyzed. We have just done the simulation. The simulation results can be shown here. See, these are the 4 access categories. AC0 is the maximum one. See, that throughput keeps on increasing, whereas AC1 and this one drops down. So that is something that we have got. Yes, we have not analyzed it.
So this analysis that you have done is for saturated stations, right?
Saturated traffic condition.
Have you done anything for non-saturated stations?
Yeah, not for this. For a legacy 802.11, we have done non-saturated. But with MPR threshold, we have not done. But I think we had some result for, again, simulation, not analysis, of course. For Pareto as well as Poisson, we have just looked at how it behaves. We have not done analysis for non-saturated. Again, that will amount to, we can borrow the way we did it for the classical 802.11. You will have additional state here. For example, we had a state like this one. Here what happens here is, as soon as there is a success, you go here and it starts an immediate packet transmission. That is what happens in a saturated case, because you have infinite number of packets, you can start a transmission immediately. So this is how we can have the model. But if you have an unsaturated case, as soon as a packet transmission gets over, you go to a state and wait and check whether there is a packet or not. If not, you wait for a packet arrival. And till the time you wait, and if there is a packet arrival, you get into it. That is the main modification you have to do for unsaturated case. So, and there the transition probability is lambda and so on, Poisson arrival rate. For using that, you can do it.
So any insights on like how much extra you can get, throughput you can get over saturated throughput if you...
No, saturated, if I am correct, that is the one that maximum throughput it gives. Because unsaturated means you will have lesser packets waiting, the throughput will be less.
Because the thing is, when you are at saturation, you would spend time waiting, and
Collision,
collision. So
yeah.
you are wasting airtime in
Yeah.
both cases because
Yeah.
of collisions as well as
Correct.
waiting.
I understand that.
And if you are actually just below saturation, you can actually squeeze in more throughput a little bit, and depends on
Yeah, correct.
parameters.
That is correct.
So what is saying that there is probably
Yeah, correct. I understand.
arrival rate where you have the probably highest throughput, right? That is not
Okay.
saturated.
Yeah. Yeah. That's quite. That is also one side of story. That is correct.
And second question I had was like, usually for all these AC and beyond, like you have frame aggregation. So any thoughts on how this works well with multi-packet reception, like
And frame
works
agree.
with frame aggregation?
Yeah. I just want to have slides for that. Can you just help me in getting the other slides? What is it written, sir? 802 point. Yeah, correct. Yeah. So this is what I was thinking of covering, but could not cover. So you will see that in 802.11 AX, so these are just the OFDM model and other things. So you will see that here you have a hybrid access where there is a partly it is scheduled access. Some nodes are scheduled access. Some have got a random access. So they have to compete and tell the access station that they have got what is called as the buffer status report, telling how many packets are waiting in that one. Then the access point can give them scheduled access for that one. And there is a packet aggregation by default happens in 802.11 AX. For example, here you will see that each node, as soon as it being given a scheduled access, it has been given a time which is called as the transmission opportunity, TXOP. For that duration, it can transmit an aggregated frame. For example, here each one is the MAC layer packet data unit. Such J of them can be aggregated with one physical layer header and can be transmitted. And again for that there can be a block acknowledgement that the access point will give. So this is by default incorporated in 11AX. And again this one also, here incidentally the same analysis of non-uniform decrementation holds good. Here the number of resource units for random access is different. Okay, here in this case 3. So the decrementation also happens by 3. So what we have been looking at, analyzing it way back is now a part of this 11AX standard.
So like if I understand correctly, it doesn't affect the throughput much, because like earlier in single transmission, right, single packet transmission, you only had to wait for one packet's transmission to acknowledge. Now you have multiple packet transmission.
There are
so if there is a diversity in the packet sizes, then you are wasting the bandwidth, right? So you're not able to exploit the multi-packet reception fully.
1 minute, is that question complete? See, multi-packet reception is a different thing. That is where when the channel can support multiple packets. Given a node has got here what is called as the resource unit in which it can transmit, should it transmit one packet and again go in for a contention, or can it transmit more than one packet is the question. So in 11 and onwards, standard tells that you can transmit more than one packet. Okay, but again, if you tell that more than one packet, I can transmit a very large packet and then tell that only I am transmitting 10 packets. To avoid that one, they have put the transmission opportunity, which tells that how much time in terms of 100 millisecond you can transmit. You either fit in very, very small packets up to that or very large packet up to you. But transmission opportunity is given. That was one thing that answers that packet size can be used to fool around. That is one thing. The other thing is this multiple packets being aggregated and sent has got an advantage that you don't need to compete or for every time, every packet. Once you get it, you can transmit a certain number of times. But the delay will be more because you will transmit a number of packets. Any other node waiting for the resource usage has to wait for that. And the block acknowledgement also may have a problem in the sense that has to tell which packets are in error and they have to be selectively retransmitted. So there is a trade-off between how much can be aggregated and its effect on the delay as well as throughput. I'm not sure whether that answers that. Yes, it can be done, but it has trade-off, and we have to carefully look into it and decide on the aggregation.
Thank you again, professors. Yeah. Thanks everyone for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there.